flat plate solar collectors. And if you recall in the previous chapters, we were basically looking at number one, how to calculate the solar energy depending on the location and the time and the conditions, the orientation. Then we looked at the kind of energy that would be absorbed by the plate. Then we looked at the glazing to see how much energy is going to go through the glazing and reach for the absorbing surface. Then at this chapter, we started looking at the losses. Why? Because we need to come up with how much is the net amount of energy which is falling on the solar collector that is transmitted to the fluid. The fluid can be a liquid or it can be a vapor or a gas. So what we see here in the right figure is some sort of a layout in which the tubes are embedded in the absorbing plates. So the energy falls into the absorbing plates, and the absorbing plates has a temperature distribution that has a higher value in the middle of the two, in the plate, in the midway between the two pipes. And then the energy the temperature reduces until it reaches the pipe, which is our heat sink, or this is where the energy is being absorbed. And if we look at this at a fin, then the tip of the fin is going to be exactly in the middle between them, and the base of the fin is exactly lying there at the tube side. Then we have a couple of additional resistances due to the contact resistance for welding, the walls of the tubes, and then the convection resistance inside. We've looked into this last time and tried to see how the temperature distribution can be estimated through an energy balance, which is in which we are looking at this direction, which is this X direction, which is going from, for example, from right to left or from left to right. So if this is the setup that we have, this is the absorbing plate. These are the tubes of the solar collector. The length of the solar collector is perpendicular to the page in this direction. So far, we are interested in how the heat is distributed in this direction, in the X direction. X could be, for example, in the middle of them. And because of symmetry, this is treated as an adiabatic, or it has an adiabatic boundary condition due to the symmetry that we have at this line. And then the temperature is going to drop from here to here. Basically, if it's a fin, so we expect some sort of an exponential decay of the temperature with the distance. And we had an expression that can estimate the collector efficiency factor as we got a relation definitely, and then a figure that will give us the value of the efficiency factor as a function of the overall loss coefficient, the tube spacing, and for different values of H. So that was basically what we have been doing. And definitely here, different figures or different lines are representing different values of K delta. K is the thermal conductivity of the absorbing material, and delta is the thickness. We have seen that, but before we leave last time, we've been reminded that in this condition, don't forget that there's a fluid comes in here. And the fluid comes in for heating. So it should be ending up or coming in with a temperature Ti, and toward the end of the collector, somewhere here, it is leaving with a higher temperature, To, which means that the temperature should change for the fluid in this direction as well. How to account for this? How energy is reaching to the fluid? Basically by convection. The plate is hot, and the heat is transferred to the surface and then to the fluid which is passing in. So as the fluid passes in the Y direction, it is being heated. And this is probably is what we need to look at today. Target is to see how the fluid temperature can change from the inlet to the outlet, and then how we can express this fluid temperature in a way which is easy for us to do the calculations. Before we start, that was an example that we have seen last time. The example is a direct substitution to the calculating the efficiency factor. which is f dash, that can be calculated either by this equation that we see here. I've just, the needed equations for this example have been given here within frames. So the fin factor M, which is the overall loss coefficient over K delta, and then the efficiency of the fin, tan hyperbolic M into the distance W minus D all over 2 divided by the distance M into the distance. And then finally the efficiency factor F dash is being calculated as a parameter or as a function of these parameters, the UL, diameter, width, and so on. So, and these values are being calculated. So this is what we see here. You can get this expression of F dash either from this expression here, from this equation, or you can get it from a figure like this based on selection of the right set of graphs that fit the problem in it. So it's a direct substitution into the numbers that are provided. What we need to look at today is to look at the flow direction, which is, again, the flow in the pipe. As you can see it here, is entering with a temperature T inlet, and this temperature should increase as we are moving along the pipe. The heat transfer to the fluid is occurring by convection heat transfer. And who would remember convection heat transfer is controlled by which law? Anybody remembers? For convection heat transfer calculation?
Newton's law of cooling.
Yes, Newton's law of cooling, this is correct. But in our formulation here, we need to come up with a differential formulation, meaning that we are going to take an infinitesimal small piece of the pipe and look at what are the energies in and what are the energies out. When we do that, we will find that there's a fluid flowing. So if this is our control volume at an arbitrary distance y, and it has a thickness delta y, this is definitely magnified a lot in this figure, you'll find that we have a fluid passing. This fluid, any fluid passing at a certain temperature, it has its own enthalpy. So this is basically some sort of the enthalpy associated with the fluid passing. The m dot over n is a representation. M dot is the mass flow rate into the solar collector in general. And to remind you, the solar collector, you'd expect to have some sort of a header here where the inlet water is coming in. And this header is, we have distributed tubes that are going out of the header like this, where the flow is going to be distributed, assuming that it is distributed evenly for every one of them. So if you have n number of tubes, then, and the total flow rate is m kilogram per second. So the flow rate in a single tube, we are now considering a control volume like this in a single tube. So this is going to be the flow rate m divided by the number of tubes. It will give me the flow rate in one tube, which is this quantity here, into enthalpy of the fluid, which is entering into this control volume. And the enthalpy is given here as Cp into the temperature, Tf. At the location that we are considering is y. If we are going to start, y is equal to 0 from here, and then it is moving, then this distance is y, and this distance here is nothing but y plus delta y. This is what we have learned in the analysis of heat transfer. When we look at this as our control volume, so there is enthalpy associated with the fluid entering, there's enthalpy associated with the fluid leaving, which is m dot over n Cp Tf at the location is y plus dy. And definitely the useful energy is coming, as we have studied in the previous class. This is coming, it's conducted from the plate, the absorbing plate, into the fluid here, which is basically the useful, Q useful. One note before we proceed to remind you of what we do here in heat transfer analysis is that we look at the energy balance, energy N minus energy out is equal to 0. There's no energy storage, and we're assuming it's a steady state condition. The energy N simply is m dot over n Cp Tf at y plus Q useful into delta y. The energy out is going to be m dot over n Cp T fluid at y plus dy. To simplify, we take this T fluid at y plus dy and we expand it in Taylor series expansion, which is basically what you see here down, that Tf at y plus dy is Tf at y plus dTf by dy into dy plus 1 over factorial 2 d2f by ty squared delta y squared plus 1 over factorial 3 and so on. We take the first two terms because the other terms have delta y squared, delta y cubed, delta y to the power 4 and so on. If delta y is small, if this is something like 0.01, delta y squared is going to be 0.0001. So it's a very small value and we neglect higher order terms. So we're going to represent that Tf at y plus dy in terms of this quantity here, Tf at y plus dTf by dy into delta y. Then we have the quantity here, which is m dot over n Cp Tfy. And here we have m dot over n Cp. And between parentheses, we're going to have Tfy. So this is going to cancel out with this. And then we have the differential term, which is d Tfy by dy into delta y. This is the one that we're going to retain. And this is how you can see, I mean, this is the energy N here. This expression that you see in front of you, energy N. This is energy out. Both of them are the fluid as it coming in and leaving. And this is the energy N again, which is coming as useful energy. So what we do, algebraic simplification by replacing Tf at y plus dy by this quantity. The first term Tf at y is going to cancel, and then we are going to retain the second term. We end up with the first order differential equation that you see here in front of you. M dot, we've multiplied the whole equation by n. So m dot Cp dTf by dy minus n into Q useful, and Q useful is basically represented by equation 6517 that we have taken earlier to be given by that, which is W F dash S minus the overall loss coefficient T fluid minus T ambient or T air. Assumptions are made for simplification that the fin efficiency factor and the overall loss coefficient are not a function of y. Remember, y is the tube length here. So across this distance, the value of f dash, because actually it's the fin here, which is connecting the two tubes. So the transfer of energy is basically in this x direction. So assume that in the y direction, f dash and the overall loss coefficient are constants. So we're going to read them as constants while we are simplifying this equation. We are separating variables and integrating. That reminds you, if you recall, when you did convection heat transfer in fluid in heat transfer course, and you did the analysis for two boundary conditions, the uniform heat flux boundary condition and the uniform wall temperature boundary condition, which is the case like this. So we're considering here a uniform wall temperature boundary condition sort of thing, and we are separating the variables, which means that dTf over this quantity is equal to the combination of the other parameters here into dy. Then what we do the integration. So the integration results in this, and applying definitely the boundary conditions at the inlet of the tube, the temperatures Tfi into an arbitrary distance where the temperatures Tf at a distance y. And that's why you see here Tf corresponding to y. And definitely the Tfi is the inlet temperature at y equal to 0. And we are getting this exponential term that gives us the value of TF, fluid temperature, at any distance, knowing what is the end temperature of the fluid, air temperature, the useful heat gain, this is the energy, the absorbed energy by the plate, UL is the overall heat loss coefficient, exponential, again UL, N number of tubes, W is the width, F dash the fin efficiency factor, Y is the distance in the pipe, and then the flow rate into Cp. This is the capacitance of the fluid which is passing. If we need to know what is the exit temperature, substitute Y is equal to the length of the tube. If the tube length is L, then at L, you're going to substitute it here, and you are getting the equation here of TF outer over TF inner, definitely TA and S over UL are constants, is exponential UL area into F dash efficiency factor over M dot Cp. That would remind us, or the expression that we have here is going to remind us by the number of transfer units. If you recall from heat transfer analysis, we have an equation like, definitely here we have more terms because of the TA and S over L, but we have a similar expression to that, out of which we could get the expression of the effectiveness and the expression of the number of transfer units. So it's a similar kind of interpretation when you are looking at this equation. Then what we're going to do here is that we're going to define a quantity that relates the useful energy, the energy gain, definitely, to the useful energy which is falling if the whole collector surface is at inlet temperature. What is that? The point here when we are looking at, there is energy transfer from, which is reaching to the fluid. The temperature which is reaching to the fluid is reaching at a certain input value, and it is being dissipated or being consumed by the fluid. What happens to the fluid temperature? It keeps on increasing from the inlet of the pipe to the exit of the pipe. The maximum heat transfer would occur if we have the maximum temperature difference. And the maximum temperature difference is going to be done whenever the temperature of the fluid is the lowest. Then temperature of the plate is hot, temperature of the fluid is the lowest. So this is the highest delta T, and this is the highest transfer rate. So we might assume an ideal case in which the whole fluid in the collector is at the inlet temperature. Is that true? No, it's just given us a theoretical limit. And the theoretical limit here is given us, is shown in this case, in our expression of the ratio between the useful energy gain to the useful gain if the collector surface is at the fluid temperature. We're talking about the conditions where we are maximizing or assuming there is a maximum delta T out of which we can get the highest value of Q. And the quantity here is called the heat removal factor, which is one of the important parameters that are utilized for determining the performance of a solar collector. So the definition is M dot Cp, T outer minus T inner. This is actually, or this is the actual amount of energy that is gained by the fluid. Fluid enters to the collector at a temperature Tf inlet, and it leaves at a temperature Tf outlet. So the quantity of energy, or the amount of energy, or the rate of energy that has been transferred to the fluid is M dot Cp delta T. Outlet temperature from the collector hot minus inlet temperature, divided by the energy which is falling into the net energy falling into the collector. The collector is receiving energy from the sun, which is S. It is losing energy to the surroundings at a rate of UL into the temperature difference that you see here. Accordingly, this is defined as the heat removal factor. What's next step? It's just an algebraic manipulation. Why the algebraic manipulation is being done? It is being done in a way so that we can get an expression of FR, as you can see it here, which is very much the same, looking like the expression of the effectiveness and the combination of the number of transfer units that we had in heat transfer. We're looking for the analogy just to have something that would be shown to be similar to expressions that we have dealt, or well-known expressions, or that we have dealt with before. So FR is m dot Cp, as you can see from here. Then we have A, we take the U common, so that here we have S over UL minus TFI minus TA. So that's an expression that you can see here, which is, again, when we are looking at that expression here, what we are doing, we are just doing a manipulation. So far, we are adding, as if we are adding S over UL and subtracting S over UL. We are adding TA and subtracting TA, so minus, this is as if we said plus TA minus TA, so that it looks like this. Why? Because here in the left side of the numerator, as you can see it here, it is S over UL minus TFI minus TA, which is the same as this. So this is divided by this to give the value of 1. And here we have expressions that are given as TF outer minus TA, TF inner minus TA. So here the FR has been related to all of the parameters that we see here are constants. The only thing which is changing is the outer temperature of the fluid and the inner temperature of the fluid. So this is basically which one of them would be known usually. Usually we know the inlet temperature and we are looking for the outlet temperature. Which one of them is hotter? It should be the outer temperature, which is hotter. So here you are the S over UL minus the bigger value. Accordingly, if we combine this with equation 664, which is providing us with the ratio of S over UL minus T naught minus TFA over S over UL TFI minus TA, this is going to end up with that expression that we are seeing here. FR is m dot Cp 1 or AC into UL into 1 minus exponential sort of number of transfer units. So again, we are getting closer to the expression that we have seen before as some sort of an effectiveness. This equation has been graphically represented in the figure that we see here. We are getting a value of F double dash, which is FR over F dash. We know F dash from what we had earlier, which is the efficiency coefficient. And this equation 674 can be given by the expression that we see here. In the right axis and the x-axis, we see m dot Cp over AC UL F dash, and in the y-axis we have the ratio FR divided by F dash. As you can see it here, we call it a flow factor F double dash. So the flow factor here is coming as a function of a single variable, and when you see the single variable here in equation 675, the equation before the square parenthesis or the square bracket and the expression inside the exponential, they are basically the same. Actually, one of them is 1 over the other. So here you are getting the value of F double dash as a function of one combined parameter. The combined parameter is m dot Cp over AC UL F dash, which is some sort of a number of transfer unit expression. So I'm writing here in italic that the equivalent, that the quantity FR that you can see here has an equivalence to the effectiveness and the number of transfer unit expressions that we have for heat exchanger analysis. There's a similarity between both of them. The only difference here is that we're accounting for the energy falling by the sun and the energy which is being lost from the collector as in calculating the net amount of energy. The maximum possible useful energy gain or the heat transfer to the solar collector is going to occur at the inlet. The inlet fluid is at the lowest temperature, and this is the highest heat transfer rate that you can get. And then we have heat losses, which are reducing this amount of gain. So we would then express the useful heat of the collector as, here we have the collector area, the heat removal rate FR, and this is sort of a difference between S, this is the energy absorbed by the solar energy, and this is the total loss from the collector. So it's given us here some sort of an indication of how much is the ability of the collector to heat the fluid. We're looking at inlet energy and energy which is leaving or escaping by losses. This expression is extremely useful, as we will see, because we are going to express some sort of solar collector characteristics in which we are looking at the efficiency of the collector being given as a function of the heat removal factor and the heat loss coefficient. So some sort of that, and this is going to be some sort of a general characteristic for any collector, as we will see when you are going to buy a solar collector. Before buying it, you need the specification sheets, and the specification sheets is going to have the efficiency as a function of the heat removal factor as an important parameter. And the relation from what you see here looks like a linear relation. It's not really linear because of the dependence of UL and S on the temperature, but in many cases, it is simplified to show or to appear like a linear equation. And that's why in the specifications of collectors, you can find the efficiency is given. Some of them would give it in, number one, in a linear expression, and then in a polynomial expression that has a constant, and then a first order, second order, and third order parameters sometimes. Second order normally would be good enough for this. So this is an extremely useful equation that applies to all flat plate collectors. And actually, as you can see here, it looks like the most important equation in the book, because this is going to take us to, practically speaking, looking or linking between what we see here and the characteristic equation of the energy gain or the efficiency of a flat plate collector. This is the base on which the selection of the collectors or the testing of collectors is being done. The useful energy gain here can be calculated as a function of the inlet fluid temperature. And this is important because in many cases, we don't know what's the outlet temperature. If you are able to calculate Q useful in terms of the values that you know already, which is the ambient temperature and the inlet fluid temperature, that makes your life much easier in your calculations, because the outlet temperature needs to be determined, and it will be determined, for example, you can say it's the equation that we used earlier as m dot Cp delta T, T outlet minus T inlet. But knowing how much is the useful energy would be the base to do that, and this is being done by this equation. And here there are some sort of a differences between the standard way of calculations, which is being done by the American school and the European school. The American school is given the expression in terms of Ti. European schools say, no, we're going to give the expression in terms of Tm, which is the mean temperature, which is a little bit more complicated because I don't know the outlet temperature. So I should come up with an assumptions, calculate the mean value, and go through iterations to do the piece of calculations that we are interested in. So this is some sort of a convenient representation when we do analyze solar energy systems, like inlet fluid temperature is usually known. Normally, you have water that you need to heat it, so the temperature of this water is known a priori. The losses that are based on the inlet fluid temperature are too small because the losses would increase as the fluid temperature increases. And that's something that we would know is making some sort of a source of inaccuracy to this kind of expressions, but we are going to look at this in our calculations, as you will see. The temperature increases in the flow direction, definitely, as the mass flow rate through the collector increasing, and this is some sort of a direct expression of what we call the enthalpy equation. Q is m dot into Cp into delta T. If I know the value of Q as a constant, which is the heat gain coming to the collector at a certain time, then I would say that for Q constant, and considering Cp is constant, and our equation is m dot Cp delta T, the higher the m dot, the lower the delta T, to keep Q constant. Accordingly, if you have more flow rate, the outlet temperature is going to be less. If you have a smaller flow rate, the outlet temperature is going to be high. And this actually is one way that we can play around to get the temperature of the outlet fluid. If you need to increase the temperature of the fluid leaving the collector, just reduce the flow rate. You are going to have less value of m dot, then the delta T is going to be a bit higher, and then you can have like a higher temperature at the exit, since the inlet temperature is known and assumed to be constant. So this is among the things that normally we consider for our calculations related to the solar collector. Okay, are there any questions so far?
Doctor, the presentation is freezing. Can you reshare?
Yes, I will do that. Yes, sometimes this we just get something with frozen internet connection, and let me get into this again. I would probably start to stop sharing and then reshare again. I don't know where this stop share. And are you able to see it now?
Yes.
Okay. Yeah, here we have an example. In this example, basically, we are supposed to be calculating the daily useful gain. We are going to do it for several hours of the day, so several times we are going to repeat the equation, maybe, or the analysis maybe once every hour or so, something like this. And so calculate the daily useful gain and efficiency of an array of 10 solar collectors, modules. So a module made of 10 collectors for a certain heating load that is installed in parallel near Boulder, Colorado, at a slope of 60 degrees and a surface azimuth of 0. You see what's being done here in this example? It is again trying to link or to build on what we have done from the first chapter. So you have something about the location, you have something about the slope, something about the azimuth, that it is facing south, so that you can make use of the information that you have gathered earlier. And this is probably one of the nice things about this course. It's something like the Lego. You are building something over as we are progressing in the course. I'm not sure whether you like this or not, but it looks like it's as if you are building a story as we are moving from one location to the other. So here what we have, again, calculate the daily useful gain and efficiency of an array of 10 solar collector modules installed in parallel near Boulder. And again, we are going to talk in this chapter and probably in our next time about the issue of the connectivity of the solar collectors. Connecting in parallel, connecting in series, that's something which would be interesting, and we'll be looking at that and seeing why and how this is being done and for what purpose. The hourly radiation on the plane of the collector, IT, I because it's an hourly calculation. The hourly radiation absorbed by the radiation plate, S, is being estimated. And the hourly ambient temperature is being given as well, because normally this is something that might be changing over the day. The ambient temperature changes, the amount of energy which is reaching from the sun changes, and accordingly, the outlet temperature will change as well. So we are given here the value of the hourly radiation on the plane of the collector, the hourly radiation absorbed S, and the hourly ambient temperature A, which also changes during the day, that are given in the table that you see here. The method of selections where equations 215, 216, and 59 can be used to get the value of IT. So here actually in this part of the chapter, we are not looking again how we are going to calculate these values of IT and S. That's something that we've learned how to do earlier, knowing hourly horizontal radiation. The collector orientation and the collector optical properties, assuming a loss coefficient, an overall loss coefficient of 8 watt per meter square centigrade. And at the beginning of this chapter, we have seen an example how to calculate the value of L, going first through the top loss coefficient and then the bottom and edge coefficient, combining them all together in an overall heat loss coefficient, which is UL. The value is given here as 8 watt per meter square. The plate efficiency factor, we have seen an example how to calculate the efficiency factor using equation or using a figure, is given as 0.841. This is from the previous example 651 that we have solved. The water flow rate through each of the collector surface area is given here as 1 meter by 2 meters in dimensions, and the flow rate is 0.03 kilogram per second. The inlet water temperature is assumed constant at 40. This is just for simplification because normally we know that during the day the temperature of the water changes. Suppose that you have water in pipes that are exposed to the surrounding. We expect the water to be cold in the morning and the evening, and its temperature would rather increase during the day. So this is just for simplification. It's given as a value as Ti equal to 40. Assume a controller that turns off the water whenever the outlet temperature is less than the inlet. That's something that we talked about earlier, talking about the critical radiation, which means that if you have a collector and the solar radiation is not high enough to increase the water, we don't turn it on because you'll be losing power, you'll be losing pumping power for no reason. So you just wait until the moment that the radiation is higher than the critical value. So the outlet water temperature is going to be higher than the inlet. So you may have controls of the solar collector that would allow the motion of the water turning on the pumps, for example, to be done if the temperature of the ambient is above a certain value, which means that the sun has risen enough in the sky and it started heating, and accordingly we can account for this as some sort of a control which can be done easily to the solar collector. So here we have the time from 7 to 8, from 8 to 9, from 9 to 10, from 11 to 12, and so on. And then we have the ambient temperature. It looks like a very cold area. IT value is being given here, which is the hourly based rate of energy flux. S is the energy falling into the plate, the absorbing plate of the solar collector. The overall loss coefficient into the temperature difference is being seen here, UL, Ti minus Ta. Q useful is shown, and then the efficiency is being calculated. Now, the dimensionless collector mass flow rate, I mean, the expression that we used to have in the equation of F double dash, which is m dot, which the one which is, I said, if you remember, looking like a number of transfer unit expression, m dot Cp over AC area, UL overall loss coefficient into F dash, which is the efficiency factor. These values are given to us here in this example. So m dot is 0.03, Cp of water is 4190 joules per kilogram Kelvin, collector area is 2, the loss coefficient is 8, and from the previous equation 651, we got the value of f dash either by the equation or the figure to be 0.841. So this expression is being calculated as 951. We're going to substitute in equation 675, the one I just brought the equation here again. This quantity is 1 over this quantity. So basically, f double dash is 9.35, which is sort of a number of transfer units, 1 minus exponential of minus 1 over 9.35. So the value of f dash has been calculated here as 0.948. We have f dash and we have f double dash, so we can calculate the value of the heat removal factor Fr. And the heat removal factor is 0.797. Average loss rate for the hour 11 to 12 based on the inlet temperature is going to be calculated here as, you know, the inlet temperature is fixed to be 40, and the ambient temperature from the table at this hour between 10 and 11 is 2 degrees centigrade. So T inlet is 40, the ambient temperature is 2, and the 3600 is the number of seconds we have in this hour. We are going from 10 to 11. Accordingly, the average loss rate here is going to be 1.09 megajoule per meter square hour. The useful energy is then calculated as this FR value into that differences between S, which is the energy falling into the collector. The equation is given here, 676, minus 1.09, which is the loss UL into TI minus TA into 10 to the power of 6, so that we can get the expression as 1.76 megajoule per meter square hour. So this is the kind of useful energy per unit area for the collector. The collector efficiency can be calculated as this useful energy divided by the energy falling into the collector. The energy falling into the collector, the IT, is a value that we are getting from this table at this hour between 10 to 11 a.m. The IT is given as 3.92. This is the energy flux falling into the collector. How much of this energy has been made use of? This is the Q useful. So the ratio of Q useful over the energy N, so this is energy out over energy N, it's given as 0.45. So at this hour, the collector is converting 45% of the incident energy of it into heating energy to the water, which is flowing in. Then this process is being repeated here. The one that we have done here is being repeated for every hour. From 10 to 11, that was an example. You can repeat that for every hour of the day and then do a summation for the IT values and summation of the QU. And at the end, this ratio is going to go to provide us what we call the daily efficiency of the collector. And that's what you see here. Efficiency over the day is given as 38%. This was at 10 to 11. It would probably increase a little bit during midday and decrease a lot during the beginning and the end of the day, so that the overall value would be this. The daily useful energy gain of the 10 collector would be that QU that we have calculated multiplied by 10, because we have 10 collectors. And this is the amount of energy or energy gain that you are getting from that array of 10 collectors. Probably reaching here, it was just a good opportunity to mention something about the term project that we would have for this course. It is what's written in the syllabus as some sort of a special assignment. And for this, I think we are in a position now to start talking about it. That I may assign maybe 1, 2, 3 problems. You are going to work with it in teams. There are already teams that have been formed a priori working in, who will start working on a problem which is common between this course and the other course of that's being taught by Dr. Wael. But for the rest, to do something similar that may have like a practical essence related to this course, what we'll be doing is basically getting cases, practical cases of that I'm going to take from one of our previous work, that we have an intention for water heating for the domestic sector in the kingdom. By the domestic sector, I mean that we're talking about hotels and hospitals. So I'm going to pick up samples of hotels and samples of hospitals, and every team that will form is going to take one of these cases to analyze. What do we need to do? We need to, for hotels, they are using hot water for domestic use. And for hospitals, they need hot waters for domestic use as well as for the operations as well. So hot water is something which is needed for both. What they are doing now for the hot water, in the kingdom here, some of the hotels and hospitals are using electric heaters, which are costly. Some of them are going for a cheaper option by buying a boiler and boiling water or heating water. And then the hot water is going to pass in tubes, and the tubes are going to go through different locations and bringing hot water to every room, either every room in the hotel or every room in the hospital. The 3-star hotels, for example, or below, are basically using some sort of electric heaters that are put separately for every room. So in every room, we can have above the bathroom, there is a false ceiling. And above the full ceiling, they are putting a 1.2 kilowatt electric heaters, like the one that we have that we may have at home. But big hotels, 4 and 5 stars, are not doing that, and they are doing central sort of heating for the whole hotel. So they have like large electric heater, but mainly because of the higher price of electricity, they go for the cheaper option of having a boiler. The boiler is going to be it's a heat exchanger. Basically, they burn diesel fuel, and the diesel fuel is heating the water, and you are taking the water in a net of piping system, which is well insulated to deliver hot water to the rooms. What we need to do is to study the possibility of replacing this system by solar collectors. So we need to come up, for example, I will be providing you with the number of rooms, the expected number of occupants, or from all of this, what you need is basically how much water needs to be heated every day. So that's something that we are going to do. You are going to calculate how much energy that will be needed for heating the water. And then the question would be, how much percentage of this energy you need to provide by solar energy? This is what we refer to as the solar fraction. أو الكسر الشمسي. Do you need to supply 100% of energy by solar? You can do that, but the problem is that you are going to need a large number of solar collectors. Or maybe someone would say that, no, not really. I may only supply 50 to 70% of the solar energy by solar collectors, and the rest is going to be done by diesel heating or diesel operated boilers heating, or by electric energy. Why do they do that? Because they would say that when we do that, we are going to reduce the needs of energy storage of the solar collectors. So we're going to save a little bit of money for the storage system, because we know that overnight there's no sun. So if somebody needs hot water overnight, then it should be coming from energy storage. Or in cloudy days, in winter days when it's cloudy and the sun is not appearing, you may need a backup system. So because they are going to need a backup system anyway, they would say that we should not rely on the solar energy 100%. What would determine that? It's an economical factor, which is basically what we call the payback period. If you are going to use 50% or 60% solar fraction, actually typical values is somewhere between 50 to 70%. Then you are going to pay for the solar collectors, and you are going to have a payback period of several number of years. If you have electric heating, the number of years are small, it's a short period. If you have heating by using fuel, diesel, and because diesel is subsidized, it's cheap, then you'll find that the payback period can extend up to maybe 20 years or so. So that it is this kind of exercise that we need to do. It is an interesting exercise and it has some sort of a practical size. You will operate as if you are a consultant office and a hotel owner is, or university or hospital owner is going to come to you and say, I need to use a solar collector system for my building, please make the study for me. So it is this kind of work that I expect you to do. What method that we are going, or what procedure that we are going to do, the method that we are going to do is called the F-chart method. If you need to get an idea of the F-chart method, you need to look at chapter 20 in the book, which is a part of the applications. I'm going to dedicate a class talking about the F-chart method, give you the procedure for that, and probably toward the end of that class, I may refer you to a software which can do this kind of calculations. But you need to go through the hand calculation at least once so that you can get the feeling of how the calculations are being done. I would assume that you are going to enjoy working with this project because it's some sort of it's an engineering practice that you may like. What we are going to do basically, we are going to use the F-chart method to calculate the solar fraction. How much energy are we going to supply by the solar collectors? I mean, as a percentage, is it 50%, 60%, more or less like that? The software is going to be an enabler for us to do something more than that, which is when we do that, what about the economics? That's something that's we're not going to do by hand. We're going to do it by the software. How much fuel we are saving this way? How much oil? I mean, it can be given in terms of barrels of crude oil. By using the solar energy, how much saving that we have done in the kind of oil or petrol or naft which is there, and how much saving of the carbon dioxide emissions that would have gone to the atmosphere if we used electricity or diesel. Why there is electricity associated with CO2 emissions? Who can tell me? When we are using electricity, are we sending CO2 to the environment or not?
Yes.
Yes.
Why?
Majority of power plants burn fuel.
Exactly, because of the power plant. So because here in our rooms we are having electricity coming from the wall, but there is somewhere there is a power plant which is generating this electricity and it is being transmitted to us. This power plant is utilizing heavy oil or light oil or even natural gas. So there are some sort of air pollution which is occurring due to the having that solar collectors in. We don't have enough time for this course, unfortunately, to go deeply in the PV, but in your program, you have been exposed to the PV, I would assume. And the PV is another way, which is in a clean way, you can generate electricity. It definitely generates DC current and you have to use an inverter to convert it from DC to AC. You have to have batteries for the energy storage or have your system connected to the grid anyway. But typically, if we are not using PV, and you know that this is a part of the vision 2030, that about 50% of the power requirements for the kingdom are going to be done by solar energy or PV panels. So there is a lot of expansion in this area, but still we are going to utilize or rely on the fossil fuel for a few decades before we totally depend on the solar energy and then save the fuel maybe for export or so. So I'm going to provide more details about the project once I'm able to cover the F-chart in one of our next classes, inshallah, and then you can get your hands started in this. Maybe before that, you would think of making groups. Every group would be of 4 persons. So let's put a target. We expect to finish chapter 6 on Wednesday, and then next Monday, I'm going maybe to dedicate the class before we get into chapter 7 about the concentrated collectors. We can talk about the F-chart method. And then you can get in with that, and then your project can be done utilizing either flat plate collectors or even evacuated tube collectors. That's something that you can do, and it would be interesting to do this kind of project then, inshallah. So some observations are made out of the example. Actually, it is the example process that remind me of the F chart, because we have something which is similar to this kind of table operation. We do calculations for every, actually we don't do it for every hour, but we take the averages for every month. And so we have, instead of talking about the time, we talk about the month, January, February, March, because you need a solar collector which is going to operate with you the whole year, not only for a day or so. So that has been reminded me, or that reminds me of that issue of the project to talk about. So some observations that we have that are made from the example, that we have basically collected a one-cover non-selected collector. This is based on the information that are given in the problem. The value of Ti is not always constant. This is the inlet water temperature. In this example, we have taken it as 40. 40 is a high value, that's number one. And number two, the value is not constant throughout the day. It will vary, as I mentioned, from morning to noon to afternoon to evening. The losses are both thermal and optical. Early morning and late afternoon, we have high losses. So the amount of energy coming by the solar is not enough to do, and this is why we talked about the issue of critical radiation, that below a certain value of the radiation flux, you turn off your collector. You don't need to pump the fluid in because you are going to lose energy. Maybe the temperature of the fluid is higher than the outlet temperature after passing by the collector, and it will be a loss to do that. You're going to consume electricity in running the pumps, and at the end, you are not going to get heating at all. So that's why the control system would allow the pumps to operate when you reach a certain temperature, for example. The collector should not be operating during these periods, even early morning or late evenings, to make sure that it will only operate when it's going to heat the water. The daily efficiency can be based on not the whole day, but if the solar collector system is going to operate for 6 hours, 8 hours, 10 hours, depending on the season, you can calculate the efficiency based on these values. I don't have to calculate the efficiency 1 hour after dawn, or just the same hour at the sun rises, because this is not really useful. Or the last hour of the sunset, I don't have to run it there, because the amount of solar energy which is coming in is small. It's not enough to take the load of heating the water, so there's no point of taking this in our calculations. If we exclude that from the table that you have, you are going to end up with a higher efficiency, because you would be eliminating the hours of low energy flux coming in. As the collector inlet temperature is reduced, the 2-day-long efficiencies would approach one another, actually, which means that, and that's something probably is behind the operation of like the F-chart method, which is talking about daily averages. The small variations day to day are not going to affect the performance of the collector a lot. If the sun is stronger there, the inlet temperature of the water will be higher. If the sun is weaker, the inlet temperature will be lower. And accordingly, it balances each other. The collector efficiency is a single parameter that would have system characteristics, and it's normally, it's not reliable for making comparison. Talking about the efficiency here, or single parameter efficiency being higher or lower, that does not say that this collector is better than that collector. The temperature of the fluid rise through the collector can vary between a value of 8.5 in this example at noon to 2.5 in the afternoon. This is relatively low temperature rise. in liquid heating. In air heating, it's a little bit higher. Basically, you have to put something in your mind that heating a fluid, the fluid is liquid or the fluid is gas. There's a difference there. And the differences are because, for example, let's compare about water and air. And this is something that we have seen a lot in our experiments when we are dealing with solar energy. I use solar collectors a lot in water desalinating areas. And one of the technologies for desalinating the water would leave that choice for us. Do we need to heat the water or heat the air? Heating the water, the delta T is not large. But heating the air, it's very easy to get a collector and raise the air temperature very quickly to a high value like 100 degrees or sometimes more. What is the issue here? Remember that CP, specific heat for the water, is around 4.2 kilojoule per kilogram Kelvin. But the specific heat for the air is about 1.05. What's the specific heat? It's the energy needed to increase the temperature of the fluid by 1 degree centigrade. So water needs more than 4 times the energy to heat it 1 degree centigrade compared to air. So it's very easy to heat the air, and it's a little bit more difficult or challenging to heat the water. You need more energy. This is on one hand. On the other hand, water can carry the energy efficiently than air. We have problems in our systems that I have a system and I connect the air, air comes into solar collector, I get the air out of the solar collector at very high value, 100 degrees centigrade, where I needed only 80, so I get 100 easily. But at any bend, at any expansion, the air loses this energy very easy. Water, it's difficult to heat it compared to the air, but it keeps the energy in. And that's why in many of the air conditioning systems, for example, which are used for buildings, some of our buildings here, or most of the buildings, are going to have different air conditioning systems that you have a vapor compression unit for the air conditioner where the Freon or the refrigerant is used to cool down water outside the building. Then water is carried in pipes into the building. For every floor, there is a room called the air handling unit, which is a heat exchanger. The water passes by the heat exchanger and we bring air, usually recirculated air, to pass by the heat exchanger to be cooled, and the air is distributed to different rooms in the building. But the medium that we have selected to bring the cold water from the AC unit, which is somewhere at the corner or outside the building, to be distributed to every floor, we selected water. Because water is flowing in small pipes, it requires lower pumping power, and it keeps the energy with it, whether it is high temperature or low temperature. That was a side issue, but I thought it's important to mention it when we are talking about the differences here in terms of the delta T you expect for the fluid. If you need to have higher temperature, reduce the flow rate. But if you reduce the flow rate, the value of QMH may be lower as well. So the relatively modest temperature rise is typical for liquid heating collectors. The temperature rise can be increased by reducing the flow rate, but that's going to reduce the useful gain to the collector that you have. And sometimes it will not do the required, you need to heat a certain quantity, a certain flow rate of water from temperature TFI to temperature TF out. So there is a flow rate that you have to deliver at the end. If the flow rate is halved, then the delta T would be increased. And you may then, if you need to be more accurate, if you have the flow rate changes, then you may change from laminar to turbulent, or from turbulent to laminar, or the value of Reynolds number would change. And if changes, then the heat transfer coefficient is going to change. So it has its own consequences if you need to do the kind of correct or right estimation, right calculations. And then the FR value can change as well. So the efficiency during an hour, if you are going to change the flow rate, can drop from 48 to 46. So you are changing the flow rate to increase the temperature, but the efficiency drops, which is not helping a lot. This is the sequence of equation that we have seen earlier, looking at the value of useful Q and how this useful Q has developed as we are getting the kind of detailed expressions of the transfer of heat in the x direction from pipe to pipe, which is a fin-like expression, or the change of the fluid temperature from the inlet to the pipe to the exit of the pipe until we reaches the expression of QU that is given as a function of the heat loss parameter, which is FR. So this is sort of a sequence that we have gone through in our analysis so far. The critical radiation level, we're not going to cover it in details, but for you probably it would be at least enough to begin with, knowing that at a certain value of radiation below a certain quantity, you better turn off your collectors because there's no effective heating for the water. And it will be a loss of energy to operate it in, at least pumping power. You are going to lose it. You are going to operate the pumps for nothing and you are not going to get a heat gain. So below a certain critical value, it is not recommended to operate or to have flow through the collector. Mean plate temperature. This is another interesting thing because if we're going to do the analysis, you know, some of the properties that we have are functions of temperature. Accordingly, we would need how to evaluate the properties. Ideally speaking, we can say evaluate it at a mean temperature between inlet and outlet. So how to calculate the mean temperature? It's being done by integration of the temperature distribution from inlet of the pipe, L equal to 0, to exit of the pipe, L is equal to capital L. It is this equation 663, which is in the frame here on the top left, on the top right. That's something that we've seen this equation earlier, and this is the one that needs to be integrated from 0 to L. Performing the integration can get us a mean fluid temperature, and the fluid temperature here is being given as a function of the inlet temperature, TFI, and then we have the useful Q area, heat removal factor, overall heat transfer coefficient of the unit, and then the F double dash, which is the efficiency parameter. So this is some sort of a proper temperature to evaluate the fluid properties. If you need to come up with what is the to get the whole details, what is going to be the value of the CP, what's the viscosity, what is the thermal conductivity. I mean, all of these parameters that are needed are better evaluated at a mean temperature, and this is a way to calculate or to estimate the mean fluid temperature in a pipe that has been done originally by Klein at 1974. When a collector is operating correctly, providing useful energy, the mean plate temperature is going to always be greater than the fluid temperature. Basically, the absorbing plate is heated first, and then that heat is transferred to the fluid. So we expect always that the absorbing plate to be at a higher temperature compared to the fluid, and then heat will transfer from the high temperature to the low temperature side. In the equation 693 here, you see the expression of QU as given as a function of the mean temperature. And I would probably have mentioned something that the efficiency of the collectors is given in figures for companies that are producing solar collectors to the American system based on the inlet temperature. In the European system, it is based on the mean temperature. So that now companies, when they are producing their unit, they try to give the efficiency expression in both so that their collectors can be sold in Europe and can be sold in the United States and the rest of the world as well. I remember when we were working, we had a brand of solar collectors that was made in Italy, and it was originated in Italy, but there is a factory which is producing it in the United States. So it was given the efficiency expressions as functions of the inlet temperature for those in the United States, and given the efficiency in terms of the mean temperature for those who are in Europe. And that was some of the issues that we have to take care of while we are doing our estimation of the efficiency and the required calculations for number of collectors and so on. Now you can get sort of a relation between both, between the mean temperature, plate mean temperature, and the fluid inlet temperature by combining these equations 693 and 676, which is in having the red frame, and it would end up with this equation 694 that has TPM as a function of T fluid inlet temperature, as you can see it here. Approximate values, I mean, the process is basically iterative. So which means that you start by assuming a value for the mean temperature, evaluate the properties, try to do the calculations, and at the end, when you get the outlet temperature, you calculate the mean temperature again, and you see, is it too far from the value that you assumed or not? And then you go through trials and errors, iterate again and again. Normally, convergence is done after the second trial, so just do it as if you are doing the experiment or the expression calculations twice. So approximate values of FR, F double dash, and QU are being used to get a new mean temperature from equation 694, and then you use that expression to calculate a top loss coefficient. And then the value of UL is used to calculate FR and F double dash again, and you are going to repeat the process until conversion is being done. And usually, normally, a single iteration would be good enough, and you would not need a second iteration for it. That definitely is going to depend on the experience or the kind of initial guess that you are going to put for your values. Some guidelines are given here. A reasonable first guess for TPM for liquid heating collector operating at typical flow rates between 0.01 and 0.02 to be TFI plus 10. So the first assumption we're going to say that TPM is going to be the inlet fluid temperature plus 10. If you are talking about air, it will be the inlet fluid temperature plus 20. Again, why 10 and 20? Because the CP values for the liquids is much higher than that for the air. So you expect air to be heated to higher temperature easily. And that's why the estimation here is the inlet fluid temperature plus 20, whereas that one for the liquids is only plus 10. An example that we can use for closure here would be find the mean temperature and plate temperature for the hour 11 to 12 of the previous example. For a value of UL of 8, F double dash is 0.948, FR is 0.797, and Q useful as 1.42 megajoule per meter square hour. If we substitute that in equation 692, you can get the value of T mean. 692, to remind you, this is the equation that provides us with the mean fluid temperature. As you can see it here, it's been given as a function of the inlet fluid temperature here. And doing that, you can get the value of T mean as 43. The mean plate temperature can be obtained by equation 694, which is this equation, gets the plate mean temperature as a function of the inlet fluid temperature. And when you do the substitution, you get the value as, you can see here, 53. Look at the difference between them. It's about 10 degrees. And which means that the first guess of 10 degrees difference between the fluid mean temperature and the plate mean temperature is something which is working fine here. In this example, we used an oversimplification, saying that UL is independent of temperature, which is not the case. UL has a combination of convection heat transfer coefficient, H, which are depending on Nusselt number, that depends on the Reynolds number that has properties, rho and mu, which means that we expect the value of the UL to change with temperature. However, it's not a strong function of temperature, which means that assuming a constant or a value which is independent of temperature can give an acceptable kind of assumption. That's the rest, which would be section 610 is just reading, as well as section 611 that talks about the dust and shading effects on the solar collector. And the heat capacity effect, I just talked about it quickly here in this, talking about the heat capacity between liquids and gases. That's something that we talked about already. So that we reached to this, to the end of this class today. What do we expect in our next class is we're going to come up, or we are going to continue and complete chapter 6, which is talking about the flat plate collector. And one of the important things that I expect us to look at in our next class basically is going to be related to the issue of, practically speaking, what is the expressions related to the efficiency calculations, or I'll probably bring you some of the standard sheets for some of the commercial solar collectors so that you can look at how much or how the efficiency of the collector is expressed commercially. So that would be it. Regarding the exam, the midterm, I've gone through about 67 or 2/3 finished the grades. Hopefully by Wednesday it should be ready and be distributed to you, inshallah. Questions?